instance, the light by light from pi zero exchange in various models, which are quite different numbers. So you can actually see that even though the numbers are different, in all the places where they are tested, the models, they agree. So this is showing, for instance, where the uncertainty comes from. The difference in this one here is that this tail is bigger than this one, which, for instance, was the enhancement that Arkady found in his way of looking at the pi zero exchange. Well, that was done afterwards. Back to Copenhagen. People who know me know that you don't escape Belgian stuff, and Schimel was no exceptions. This is a specialty from my home province called Limburgse fly, and Schimel has eaten many amounts of these during all his visits.
I can see that the bottle of wine is empty.
Okay, in Copenhagen we also did a few more things. We worked together with Eduardo on light quark masses, where we managed to get the error down quite a lot on M up plus M down compared to then existing calculations. We also did K2 pi pi, one loop chiral perturbation theory. This had been done earlier, but calculation managed to have been fully lost, so it had to be redone. Here we also showed that the lattice main part, new part of this paper was that in lattice gauge theory calculations, you cannot get K2 pi pi from K2 pi at next to leading order. We also work, for instance, also on nonleptonic matrix elements where you don't exchange W bosons but photons instead. And here we discovered that the low energy constants were actually gauge invariant. I already knew that you had to be very careful in defining quark masses in order to be able to do a long short distance separation. Here in this paper we discovered it was even worse. So the separation between long and short distances, so the chiral perturbation theory electromagnetic low energy constants are actually the gauge, electromagnetic gauge dependent. This was found simultaneously actually in Paris. So when he left, he went back to Valencia for 1 year, and then 2 years later got a permanent position here in Granada. And he was about to become full professor. I don't think he managed to officially become it. He died before. But as you saw in Tony's thing, he was basically coming more or less once a year for an extended visit to Lund. Most of the time he was working, but there were other things around. The beer was not visible. One of the things I told him that Trappist was one of the best beers in the world, and I think he managed to teach this on to his wife. Non-leptonic matrix elements was already mentioned that we have worked a lot on together. I would call this the X-boson story. So one of the problems is when you do this is in fact to get a correct way to calculate long distance approximations in a model and do the short distance using the renormalization group from QCD. You can do this with green functions, or alternatively, for instance, look at the pi plus pi zero mass difference. You have to calculate for this photon overall q squared gamma momenta. Now here you have a physical photon, so here you can just say, okay, I do this. Split this integral in two. When it's a high momentum, the pions are so soft that it really has to go back through quarks or gluons, which gives you that the short distance piece goes something like 1 over mu squared, where mu squared is this shift over scale from long to short distance. For the long distance, several models were done. Vector mesons was done by these three. The chiral constituent quark model was done by the previous speaker and me. With Schimel, we did the ENGL model. So this allows, basically the point is that this flip over scale is physical, so you can identify it. So the problem now is for the weak interaction, you have 4 quark operators, so you have to do something to physically identify this scale. So what we did was you introduce a set of things like the photon, which reproduce the short distance 4 quark weak operator by exchange of these bosons. And these are the ones we called the X bosons. But when you do that, you have the short distance matrix element, where you have the running plus an extra thing from coupling to quark matrix, external quark legs. This depends on your external states. We approximate now this point here by exchanging our fictitious X bosons and calculate the matrix element between the same states. So this then allows us to match this thing here, where this number is also dependent on which states you put here. But if you calculate the coupling of this X boson coming from comparing with this here, you find that all this scheme dependence and all this trouble in how you identify the four quark operators goes away when you do this correctly. And that's then how we ended up calculating the matrix elements afterwards. The delta equals a half case is a bit more problems. You have 10 times 10 matrices instead of one number. But again, you do the same thing. And when you do that, you get for his favorite number bk in the chiral limit this type of long distance contributions, and away you get this type of long distance contributions. If you match this together with the short distance, away from the chiral limit you get this number, and in the chiral limit you get this number here, and that you get some reasonably good determination of the short parameter b hat k. Epsilon prime over epsilon, we got very good matching in the imaginary parts, which this is, for instance, the imaginary part of the octet. And if you calculate, we got so G8 and G27 roughly right, so we get more or less within 30% quantitative explanation of the delta equals half rule. And for epsilon prime over epsilon, we had the opposite problem of everybody else at the time, is that when we plug in the number, we get some number like 5.4. If you include isospin breaking corrections and final state interactions, we get it down to something like 3 times 10 to the minus 3. And this was, at least for us, the indication that the standard model has no problems reproducing the measured value of epsilon prime over epsilon. We have been together in very many conferences, got lost on some mountains as well. One of our better ones was actually managing to get separated in Benask, and then after 1 hour each just happening to walk into each other again. Typically Chimo. Since then, we've been working very much also further improvements. This Tony said, for instance, he wanted to produce a number recently. We, together with Elvira, worked with this almost 10 years ago by now. This gave numbers compatible with our earlier NGL calculation. We worked extremely hard trying to improve on the NGL model. Basically, the idea was that you can either do something like what Eduardo talked about, adding more and more resonances and trying to fix older couplings in various green functions. We said, well, the NGL model works very fine. Why don't we just replace these one-loop functions, which have the problem cases, by polynomials in Q squared? If you just put them as a first order, you get something which is very much like the NGL model and works extremely well. If you try to expand this, it didn't work. After a while, we realized that if you try to do this, that you get higher order poles with the wrong sign residues. And this is a problem that many models trying to extend the NGL model have, except that they hadn't realized that there is a physical problem with this simple afterwards. We also realized that this problem with finite number of resonances, even for things which are very simple in perturbative QCD, like 0, you can need an infinite number of resonances to saturate. For instance, if you take a PSP 3-point function, the short distance piece vanishes without chiral symmetry breaking. It's proportional to Q by Q. But once you include that, it looks like this. If you try to reproduce this with the sum of resonances, you basically get 1, 2, 2-pole and 3-pole contributions, and then the couplings are or polynomials in the other ones. Now, the problem is, what you can do is whenever you have a green function, you can use with the LSZ theorem, use it to get at form factors. You have QCD constraints also on these form factors. These are, you could call Brodsky-Lapage constraints, or they follow from even simpler quark counting rules. Now, if you look at things like this here in the short distance, oops. You see that it has not only poles at short distance coming from large Q square, but also these p squares in the top in various terms. This tells you that if you do this sum with a finite number of resonances, you should have form factors which necessarily increases like the Q squared going through the form factor. And that, you know, is not true from these quark counting rules. So you have a clear conflict with a finite number of resonances. I show this for a very simple green function, but you have this short distance behavior problem in just about everything which has 3 external legs or more. And that's why we got stuck for a long time. Elvira and Shimo, with some help from me, worked rather hard to try to get some decent model anyway for BK. In the end, we didn't manage to get the error down very much because the intermediate region is rather uncertain. There was no good way to generalize this to current quark masses, so this work has somehow stalled since then with that. Shimo went to many conferences. Example here is Euroflavor 2007. If you go to many low-energy flavor conferences, you can find pictures on the websites where you can find Shimo. This contains several more people. We were here. Santi is here. Well, that's me. Well, that was one of the earliest speakers. And I think this character, I've seen walking around here too, but I'm sure there are a few more. What have we been doing? I'll show you a little bit about G-2. We've had this problem is we should try to really do G-2 with a better hadronic model. And both Shimo and I and several other people have large amounts of notes, but none of this ever got really finished. We're still stuck with this better intermediate energy model, which we looked on a bit every time. And we thought of doing a short calculation for K to pi L plus or minus, but we have been stuck for 4 years with non-chiral invariant results for the matching piece, and neither of us can find a mistake in the calculation. So probably here was one of these obstacles which nobody else noticed before flying around still. His last visit to Lund was in 2008. And as you see, we try to enjoy life together too. There are several bottles standing around here, and as you see, Belgian pie is still around. Okay, let me conclude here. He was my most frequent and longest term collaborator. I mean, we definitely became friends. The number of conferences where we have enjoyed dinners and beers and glasses of wine and walks together, I tried to count, but I stopped when I reached something like 40. We have had times together in longer term visits, Copenhagen and Lund, Granada, Benausk, Seattle, many conferences, many Flavia networks. And I must admit, I was looking forward to giving this type of talk, but I had hoped that it would be at his retirement symposium, not at his memorial symposium. Thank you.